context, and then different faculty and a couple of students will be giving additional lectures over the next couple of days. What I'm going to talk about is what we call ultra-coarse-graining, and you'll understand in a few minutes what I mean by that. Coarse-graining is basically the process of turning molecular structures into simpler-looking structures, and here's some little pictures. This happens to be an actin, or a piece of an actin filament, so these are whole proteins, and this is going to be an important application that we'll talk about. Here you can see a simple helical peptide, which is coarse-grained. The whole purpose for doing this coarse-graining is to really be able to boost up its scales, because we know fundamentally that there's a lot of stuff happening here at a cellular scale. If you don't recognize this as a cell, these are actin filaments, so this is the cytoskeleton. You could pick many different possible cases like this. You could pick materials, some sort of self-assembled materials or polymers, but we have focused on this particular problem that's really quite challenging. And these core filaments, of course, are made up of these proteins. This is the so-called G-actin, the monomeric actin. And they assemble into filaments, often actually more complicated. They branch, there's different proteins that bind to them, there's a whole host of different things that interact with membranes. But the core filament looks like this piece. And what characterizes this protein are some very important features. You can kind of see, we'll come back to these, you can kind of see 4 domains. Actually, the orientation of this guy is rotated by 180 degrees from what I'm going to show you before. The next, I should say, this region is quite important. In here is where the ATP binds, so the nucleotide, and that undergoes hydrolysis. This filament, in some mysterious way that Martin McCullough is working on that you'll meet later today, it accelerates the ATP hydrolysis by about a factor of 10,000. That plays into its flexibility and its ability to depolymerize and other things. So all of that, if you do simulations, and we did them using molecular methods, so molecular dynamic simulations, and you put water around that, which you certainly would need to do at that level, you'll hit 1 billion atoms in a heartbeat. Okay, so even though 1 billion atoms we can sort of do now, it's pretty challenging. So to ever, I think in any of our lifetimes, to ever be able to go up to this kind of scale, you need this coarse graining. Okay, and the coarse graining is both needed, but also the correct thing to do, because even as complicated as that looks, it does not matter what every single atom is doing in there at a given point in time, right? So you know, let's say 10 to the 23rd of all of atoms. You don't need to know what all of them do. We have some limited set of experimental observables that we look at, and this is an intermediate representation. Okay, and the hard part is figuring out how to do these mappings and how to give meaningfulness to their interactions. Okay, so not have them just be toys, models that you sort of hook up stuff and you see what happens. And that's what this center is about. This chart, which I'm going to refer back to multiple times, organizes all of the effort in our center. I know that when your mind sees a chart like this, the first thing it does is shut down because there's too much information on it. But let me kind of lead you through the flow of our intellectual work here. These problems that we want to look at that are really big, and I'm going to show you some examples of them. It's virtually impossible to start with a very pristine bottom-up approach. So you start with all the atoms and you systematically simplify the problem. You have to kind of have a hybrid approach where you come in from the top and the bottom. And that's what we're doing. So this is really a flowchart of intellectual effort of really integrated methods. We always start with taking whatever experiments we can possibly get our hands on. Okay, and the more the better, really. And these happen to be some electron microscopy images of 2 actin filaments. One is older, it's aged, and one is newer. Then we develop these coarse-grained models, and I'll talk a lot about this. We are developing here what we call ultra-coarse-grained models. You can see this is a very simplified model, a little more elaborate than the ones I was showing you before, but there's a ton of protein described by this coarse-grained model. In fact, actin has 375 amino acids, and this has 12 of these coarse-grained particles. So you're mapping 375 amino acids into 12 particles, all right? And then with these models that are developed through mappings and also sort of physical reasoning and experimental data, we start carrying out very large coarse grain simulations, and I'm going to show you some examples of that, what they can tell us. And with those simulations, which have actually turned out to be a greater challenge in their own right, and I'll give you 2 or 3 slides of the challenges that we faced with that, we can go downward in scale then. Okay, so downward in scale to begin to understand where are the important regions, where these proteins associate, where are the binding interfaces, what's going on. And then dive really downward into the atomistic scale. And so my colleagues tomorrow, Benoit Roux, Aaron Dinner, will talk about, will introduce this idea of how to sort of bridge the coarse grain down back to the atomistic scale. And then this finishes with taking all of this information we gained and putting it into a new theoretical framework. So even we start out with relatively simple coarse grain models, we end up with far more elaborate ones with more physics in them. And then you can see that you can keep looping this, right? They can make new predictions. If there's not new experiments, you go back, feed in, and you keep going and going and going. So this is a self-contained intellectual loop, if you will. Okay, so I'm going to start with talking about coarse graining, and I'm going to start with talking about the pristine coarse graining. Okay, I'm going to talk about if you could do it right, if you didn't need to sort of come at it in different directions, how would you want to do this? Well, this is what coarse graining is about, at least in our hands. It's not always done this way. Many people view it as a kind of a computer modeling, but we're trying to base it on good statistical mechanics. And by that I mean some sort of a theory. This is the most common one I bet all of you have learned, that if you can do the calculation of the partition function, this is written in the classical form, right? We're just integrating over many, many degrees of freedom. This is a big vector of all the particle positions. We'll connect to the free energy of the system, and there's other sort of substructures here, distribution functions, things like heat capacities, other thermodynamic quantities that come out of this calculation. And this is really, really a hard challenge, even though every year the techniques, the ability to do these atomistic calculations keeps improving and improving and improving. The computer gets bigger, the free energy sampling algorithms get better. That's all good for us. We're happy about that. But what we want to do is map this calculation into a simpler one that involves fewer variables. So this is a coarse grain mapping of this is a hairpin peptide, a little structure here. And we're turning these amino acids into these funny beads. And in our hands, there's an actual mathematical mapping. So those atoms get mapped into the position of that. So the best way to understand that would be the center of mass. You all know how to calculate a center of mass. And so that bead, if you will, I have no idea why we call them beads, except I suppose they look like beads on a necklace. But those coarse-grained beads, that thing represents the center of mass of all of those particles. Okay. So some of the really hard problems, the 2 hardest are, it doesn't matter what level of this work you're doing, is what's the best mapping. And this is a deep, deep problem, actually, because you don't want to overdo it. You don't want to oversimplify your problem so much that you've lost essential physics. So if I had mapped this whole thing into one bead, you can see that I would, it might be useful. Maybe I care about how they all, 1,000 of them aggregate, that's all I need. But it's likely that would have been overdoing it. So the information content that you lose is really important. And then the other problem that I told you about is, how do I understand once I've done that mapping, how do these guys interact with each other? Because it's no longer the potential energy function. And we've worked very hard on this problem, and you'll see we continue to work hard on that. So I'm going to lead you through just a couple of very simple mathematical steps to show you how to understand this from the most fundamental way. Again, we start with this theory, which is a good one. We do these insertions of these mappings. So the mapping M is the mathematical function that maps the center of mass of these guys. This is understood to be a product of these delta functions, many of those. So it maps the atomistic positions into this place. And then, you can always insert an integral over a delta function because it's equal to 1. You can put it into the equation. It won't change anything. Then you switch the integration order, and you impose then this condition. It's understood the normalization factors for different number of particles, the so-called ideal gas normalization, is folded into these definitions. And if you do that, you identify what this coarse-grained interaction should be. And it's a very challenging problem to calculate. I have to apologize to all of you over there. I think I'm going to be looking this way. but I'm going to keep reminding myself to look at all that. So, and also the screen's bigger so I can see it. So what this is actually a very hard function to calculate straight up. It's what we call a potential of mean force. What it would be if you could do the calculation sort of as a frontal attack is you would go ahead and do that atomistic calculation I mentioned here, right? It's still in there, but it would make life even harder for yourself because with this delta function you would only record data when this condition was satisfied, meaning that the mapping was at the point R in space for the big coarse-grained variable. So this is an impossible calculation to do directly, but it does tell us in a perfect world what exactly this thing would be, and that is a potential of mean force. It's a free energy function, okay? Why? Because you see, I've integrated, just like this is the free energy, this is a conditional free energy with these mapping functions constraining the configuration state space, but I'm still integrating over all the motions of the little guys, the little r, which means their entropy, their fluctuations are folded into this definition. So that's a really important idea, is that this is not a potential energy function. Okay? And much coarse-grained modeling, when you download certain programs, there's the most well-known is one called Martini. They don't do this kind of calculation that I'm going to talk a lot about today. They just start here and they try to develop some models for this based on certain data. Okay, so it's a very different approach. And you know, it's successful in its own way, but it's different from what we're doing. So it turns out that you can get around that problem. This is before this center here even started, we showed that it was possible to use variational mathematics. Variational mathematics is you have a target, something you're trying to describe. You have data that is going into that, and this is the atomistic forces, right? So the real forces from the molecules, and you square it so it's positive. You sum over all those coarse-grained beads, and you average over an ensemble. It's a bit of an interesting topic about exactly what that average needs to be, but we showed that if you can represent this function flexibly enough. So if you have a way of recording this data and you don't make too many assumptions on this, you can have a very, very good representation of what I just told you need to get. That's, you minimize looking for this. In fact, if you had perfect knowledge of this, which you never do, of course, right? You can never avoid making approximations, right? You always have to make approximations. But if you didn't, okay, you would get the exact result, right? So this methodology gives us this result. And I want to show you how that works before I move on to the challenge of ultra-coarse-graining. This is a simple problem we've talked about many times, but it kind of baffles people a little bit, but it shows the sort of the physics behind this. This is turning water, a liquid of water, not just one water molecule, into a fluid of single bead particles, so as if they were argon or neon, okay? And that seems crazy to do that, right? That's, you know, these have hydrogen bonds. Real molecular water has structure. It's tetrahedrally coordinated. It's all presumably due to that. So if this approach is working, and I'm telling you about the physics of all of the real, you know, hydrogen bonding and organization in the real fluid has to pop up in the way these guys interact with each other. Right? And so in fact, this is a radial distribution function. And if you don't know what that is, that means you're sitting on one of the particles in the fluid and you look at the probability radially of seeing other ones near you, and they always look like this. This is the first solvation shell, second, third. And just to make a long story short, in this particular example, and there are some subtle issues with this we could talk about after, you know, in the questions if you're interested, we agree very, very well with the basic structure of the fluid, even having mapped it into these center of mass sort of objects. And how? How did that work? Well, if you look here, you can ignore this. This is the force. This is the effective interaction. So what the red curve is after doing that mapping that I told you about, doing the mathematics, it is the way in which many of these particles interact. In other words, they're pair potential. You still have to simulate the fluid, right? It's not a gas phase type. You still have a fluid. And what's interesting about this is it's so different from the way argon would behave, right? That's a Lennard-Jones potential, the blue one, just so you can see. And in the classic theory of liquids, what really defines that radial distribution function is this hard wall. So for simple fluids, that hard wall is just packing. You can in fact map a simple fluid into hard spheres, so no attraction, and you'll get a radial distribution function that looks very nice. It has to do with just them not being able, with thermal disorder, right, with entropy, they're packing, and they have a unique number of nearest neighbors, which is either 12 or 18. I have to say at this hour of the morning, I've forgotten. It doesn't matter. What does this coarse graining do for water? Of course, water is not like that fluid, right? Water has 4 neighbors. It's tetrahedral coordinated. What water does when I coarse grain it into a single particle fluid, it puts this big blip right in the middle of that. So you can see the physics showing up. Water is refusing to act like a simple fluid because it's not a simple fluid. I've coarse grained it. Where does that physics have to go? It has to go into this coarse grain interaction. It goes right exactly there, which so happens to be right where that first peak is. And of course, the integral over this first peak to that minimum is 4 neighbors. So you can see how the physics pops up. This big deep minimum, it kind of looks deeper and more important than it is because radially as you go out, there's all kinds of configuration space too. So it's not quite as deep as you think, but that is attributed to these structures here. So you see the physics of real water appearing in the coarse grain. So if you could do this right, that's what you would get. You would always get it. You would get it for proteins, you could do it for the big things, the little things. That would be a wonderful thing. I could retire, we wouldn't have these workshops, it would all just be done. Okay, but unfortunately that's not. I'm gonna have to skip this part. This is another example of sort of decomposing the energy and entropy terms, but I see my time is moving on. I want to get to this topic. Okay, so all of what I just told you about was basically done back in 2008 before this center came into existence. Okay, so that's not what this center is about. All right. This center is about pushing it to the next level. The next level is what we call ultra-coarse-graining, because it so happens that really at the level of what I showed you before, a few of these beads per amino acid, we'll never get there. We're never going to be able to get up to that level of biology. All right. So we have to do this ultra-coarse graining. And these you see, these are 4 beads representing 375 amino acids. And we still have the same problems, except the problems have been made more difficult. We have a problem like this where, and I have to tell you, this is probably a better model for actin. It turns out that just the 4 beads that are the big ones here is really being really overly aggressive. You need some other ones. This region is important, the nucleotides, some other stuff. But nevertheless, this is a 12 bead model for actin. We're trying to, in essence, maintain this connection going from an integral over 375 amino acids plus water to an integral over 12 particles. And you can see we have very substantial issues of how to do the mapping first and then how to do the coarse graining. So what I'm going to talk about now is sort of the first part of this. I'm going to go through everything but this last part today, and I'm going to illustrate this with both conceptual slides with things that are more mathematical, although not really heavy on the math, but also some applications to show you the sort of the power of this. So what I want to show is about sort of the first part. I'll group them together of using the experimental results and whatever physical modeling you can have to develop your coarse grain model. And I'm going to illustrate that with a problem that we've worked on that has to do with HIV replication. This is a really fascinating project and a very complex process. The way HIV sort of evolves is there's a long protein called the GAG protein. Some people refer to it as a polyprotein that has different domains. This is generated by the virus through the genetic translation process. These proteins accumulate on the inner cell wall, so this is the cell wall. They target certain lipids and they start accumulating in a way that's not completely understood, but it is known that then they start bending the cell membrane. So they start pushing what's called a bud. And at some point, eventually, there's some other proteins that are recruited, it's not being shown here, that cut that neck and this thing goes free. This is what's called the virion. The virion is a viral particle. It's made of membrane. There's some receptors on the surface and then these GAG proteins. And what happens is HIV protease is an enzyme that comes where these little arrows are. It cuts in a certain order, actually, a very well-defined order, which no one completely understands why it's that way, but they do understand that it is that way. This particular region, called the CA, the capsid domain, has an N-terminal piece and a C-terminal piece. They form dimers and then encircle the RNA. This little object in here is called the virus capsid. And I'm sure some of you have heard the phrase virus capsid. This is an example of that dimerized protein. It's a very unique looking shape. You can see these images of the capsid here, the membrane. This is what's called the mature virion. And the sort of model for this is that it forms a kind of thing that looks like a carbon fullerene. So a lattice that looks like these hexagons and some pentagons where there's high curvature. And those proteins are, the dimer proteins are organized into hexagons and pentagons, sort of half of the protein in one of these and half in the other, and this interesting sort of chiral spin. So this is sort of a picture. The pentagons like this, so there's one pentagon of proteins encircled by 6 hexagons, and then most of it is a hexagon encircled by 6. So we set out to model this, and this illustrates the first part of the procedures that we go through to develop these coarse-grained models. The first is, how do you represent the thing in the first place, okay? These proteins in solution have freedom, they have motion, they're going to bind into this lattice. When they bind into that lattice, they lose their entropy, right? So it's something that's moving freely, it binds, delta S goes the wrong direction, right? Delta S would always like to go up if it could, but it goes the wrong direction because it loses that motion. How does it compensate that for that? Those binding interfaces drop the energy, or the enthalpy, if you will, so the free energy is favorable, all right? So we want to understand this thing. You cannot possibly understand this if you don't get the basic motion of the protein right in this coarse graining. So this is a paper that came out some years ago that we still use to this day, although we're working very hard to generalize these algorithms, is that it's a different variational. This chi-squared is not the same thing as before, but what we do is we look at the basic motions of the protein and sort of the lowest frequency of those motions, which I think you can see these arrows show those very low frequency modes. And we develop a coarse-grained model that recapitulates that motion as accurately as possible. Right? The way we do that, we have I won't go over this mathematics, you can solve this algorithm repeatedly. You carve up the primary sequence of the protein into segments. Probably the weakness of this method is, to this day, the user is the person that says how many coarse-grained particles you want. So you say 4 or 12 or whatever. You don't. This algorithm is not yet smart enough. We need additional information to have it tell you how many coarse-grained particles you should have. Okay, that's a very hard problem. In this case, we have 4, and it adjusts in solving these equations which atoms go into these coarse-grained beads. And I'm going to come back to this later in the talk. This is this very crude representation of the CA dimer. Okay, you can see there's 4. You might have guessed that. This is the solution. Just shows you chi-square goes to a minimum. But for more complex proteins, this is a lysozyme. In fact, it builds this kind of funny coarse-grained molecule for you. I would challenge anybody to just guess those right positions. You can see that many of them make sense, like up through the helices here, sort of the loops in here, like this. But this algorithm automates that. So this approach, along with, I have to say, considerable insight derived from experiments, has allowed us to build a coarse-grained model of these dimerized proteins in HIV. And this is a picture of it. It's a side and a top view. You can see it's representing mostly the helices. These sort of unstructured regions are not so important because the helices are important for the packing in that virus. The other really important part, which you cannot get from an algorithm that tells you just about the shape, is the motion of this hinge. Okay, so this hinge has a motion. If you go through all of the structural database and you look at all of the variety of structures that have been determined from NMR, from crystallography, from different things, you'll see that there's a whole range of motion that they sort of map out. So the coarse-grained model has to recapitulate that, and just to make a long story short, it does. And then the last part is the attractions. This turns out to be a rather subtle problem that, this representation of proteins is reasonably high resolution. It's certainly not at the amino acid level, but there's quite a few beads. You need to get by with as few attractive interactions as possible, because in a computer program, when you do any modeling of something like this, summing over lots and lots of attractions will kill you, okay? So short range stuff that's just packing is very, very short range. You just need to know about your neighbors. But if it's an attraction, it's just like water. You have to sum over tons of pieces. And so we minimize the number of attractions to just be between the N-terminal and N-terminal and C-terminal domains in a simplified way. So what now? Well, what I want to show you is the next sort of, I'm grouping these in twos so I don't belabor this too much. Now we want to carry out simulations and tell us what we discover from it. All right? And at this juncture, we were able to take existing MD codes and beat on them pretty hard and make them kind of work. Okay, but we discovered a very profound problem with this kind of modeling, and I'll just take 2 or 3 slides to tell you about it. It turns out that when you do the level of coarse graining that we do, what I call ultra-coarse graining, solvent has to be eliminated. Okay, it's the same problem that I mentioned before with attractive interactions. If you fill up space with solvent, even if they're by solvent I mean water, basically. If they're one bead, you still have millions or billions of those, and you have to integrate over them interacting with everybody. So you need, at the ultra-coarse graining level, to go to an implicit solvent. The solvent is gone. Its effect is there, but it's gone. And what this does for you is something actually very perverse. It creates a tremendous amount of empty space. Okay, so this is this is actually a tomogram, so this is an actual experimental image. But there's other junk in the virion, which I'll come back to. There's the membrane, but it turns out that space is absolutely far less densely filled than your typical molecular dynamics simulation. Typical molecular dynamics simulation, you've got water everywhere, right? And all of the methods that have been developed for scaling those, for running those on big computers, assume that your space is densely filled. So in our problem, we had a massive load balancing problem. Some of your processors will be working very hard trying to calculate interactions here. Some will be doing nothing. All right. And so one of our postdocs here, John Grime, I will not go into this, has just recently solved this in a very clever way. One is to use a sparse data representation, so you don't fill up all of your memory with zeros. Okay. You're trying to fill up, empty space with trying to record that it's empty is stupid, right? The other is load balancing had to be done with something called a Hilbert curve. We learned this from astrophysicists. Astrophysicists have the same problem. They're simulating galaxies, right? There's a lot of them, but there's a tremendous amount of empty space. And the way they do it is they carve up space, not through just a simple cubic grid, but these fancy looking curves. This is some statue somewhere, and I know I've seen it. I think it's in Switzerland possibly. This is called a Hilbert curve. And with that, the load balancing, this is just to give you a preview of stuff you'll start seeing coming out of the center in the next 6 months. We can run these simulations that I'm about to show you over more than 200,000 processors on big computers. In fact, at some point, you distribute the work over just the cache memory on the processor, so you actually get a super linear scaling here. So we're going to be able to do these simulations at a scale that no one has ever imagined before. So we've done some, and this is the result. I want to tell you where this came, what this has led to. This is the HIV capsid. You can see it was moving there. In vitro, meaning experiments that are not in the natural system, you typically don't form these capsids, and that's really probably not even a capsid. It's more of a misfolded sheet. But what you typically get are tubes. And one of the fundamental questions is, how do you generate curvature in the tube? And it turns out that in the model that we have, the packing of the helices is robust enough that it naturally generates the curvature of these tubes. It's not obvious why that would happen, okay? Because you'd think they just stay in a flat sheet. These are 2 different views, but we actually can recapitulate this. In the theme of trying to understand what at the molecular level leads to certain phenomena, let me quickly move through something we discovered. One of the beauties of these coarse-grained simulations is you can begin to scan the parameter space, right? You certainly want to develop a model that recapitulates what's observed, but you can tweak the parameters to understand why things are the way they are. And what these plots show are scanning the energy parameters. So this is the interaction between the N-terminal and C-terminal regions, so between this and down here. This is the interaction between the N-termini, which is sort of up in here, and we can scan those net interactions and look at stability. This is a log of the root mean squared deviation from the perfect structure. So dark blue means that the thing is like cement, it's glued together, it's perfect. Yellow means it's falling apart, right? And what we discovered from this, which I think was kind of, people were thinking about this, but it wasn't really known yet, is it's really not the hexamer, it's really not the pentamer. The most important thing, you can see the regions of, sort of the important blue region is far more stable, and this region is the important sort of demarcation zone. It's a substructure. It's called the trimer of dimers. So there's one of those dimer proteins, there's another, and there's another in a triangle. All right, and I'll show you just going back where that's important. Go way back, sorry about this. If I look at that lattice, it's that vertex, you see where there's a trimer in here. And that is the important thing holding this together, not the hexagons and the pentagons. And I'll show you that, and not only that, in building the lattice, what is really important. Here, these are simulations. We cheat a little bit, I have to be honest here. So we run it on a quasi-sphere. In the virion, you're contained in a sphere. But we don't let the radial dimension fluctuate beyond a width. The proteins can move somewhat, but they can't just go freely in three-dimensional space. That accelerates the assembly. Let me show you a movie here. I want to show you. You always are forming these trimers. So you see the trimers are in blue. They're constantly forming and dissolving. And what they do actually is template the growth of the hexamers. All right. These are periodic replicas, so that's not magic here, all right? It would be hard to have that many things do the same thing at the same time. So what they do is they're critical not only for the stability of the lattice, but in growing it. And depending on whether you have a large radius or a small radius, you get more pentamers in red than you do here. Also, the flexibility of the protein that I told you about before, this hinge, determines very much whether you get these lattices. So if you treat it as rigid, like glue, so that dimer cannot bend at all to accommodate the lattice formation, you form very few sort of lattice. These are different radii, but if you have it flexible, you can see it's very good. So what have we accomplished? Well, we have accomplished doing these big simulations based on these sort of first pass models and identifying the important parts of the problem. There's one other important thing that I need to tell you about that will really drive home the need for these methods. There was a mystery as to why in vitro you don't get these capsids formed very easily. Okay, they form in biology in the cell, but not very easily in vitro. In fact, what you have to do is change the conditions. You have to put a huge amount of salt in, so almost 2.5 molar sodium chloride, or you have to change the pH to get anything to happen. Well, it turns out in the actual virus, so this is the membrane, we're kind of simplified it, there's that capsid, the RNAs inside of it, there's a tremendous amount of junk in there, all right? It carries along a lot of stuff. This is spins for, this is the amount of other stuff that is in that virus particle. So that simulation I showed you, the thing trying to grow, is happening in that kind of an environment. These are things. The protease is important, it cut this up, but this is other stuff that's not important. So you can see that when we want to go to actual biology, this is what we're going to be faced with. We're going to want to study the problem I've been telling you about, but in an environment with this, and we're going to have to coarse grain the heck out of it. All right? Because there's just no possible way to do this. And just to show you how important that is, we're constraining these proteins in the spherical virus. This is similar to an experimental setup where they use a stuff called Ficol. Ficol are little polymer beads that are crowding. They crowd just like that stuff I showed you. If you don't have any Ficol in there, poor John, who's tried to get this to happen for months, nothing happens. I mean, this is now full three-dimensional simulation constrained to be in this virion. There's no formation of this virus capsid, all right? But when you start inducing crowding, and this is kind of artificial, it's not all the real proteins, you don't have the final answer yet, but you can see qualitatively the difference. These are the number of contacts being grown. You see we're starting to grow the virus capsid shell. We're not yet finished with this. We think the final answer, of course, is the RNA should be in here too. We don't have it in here yet, and that will help manipulate this RNA that will close. So that shows you the first part. Let me finish in the last sort of 10-15 minutes of sort of pushing to the last part. What I've shown for you is, these big simulations can start identifying the important interactions at the coarse-grained scale. And now we need to say, okay, did we resolve that enough? Did we really include in our modeling what's going on at the atomistic level? Right? Or is there other stuff? Do we need to elaborate the model? And tomorrow you'll get quite a bit of information on this, what we call the multiscale string method, which is connecting these coarse-grained representations to atomistic simulations. I'm going to do it in a little bit of a more simplified way of just pointing out to you where this sort of stuff comes up. And I'm going to show you again a couple of examples from some different things. This is an example of another protein. These arch-like proteins bend membranes. All right, they're called bar-domain proteins. They look like a banana. They bind to membranes. And then here are helices. These helices stick into the membrane, so they're like a wedge. All right, so you can see this is sort of an artist's rendition. They wedge, and if they go into one side, they drive curvature of the membrane. And these are pictures. These are actually from our simulations, but there's lots of experimental images that look like it. You take a liposome, which is a bubble of lipid. You put this stuff in and it tubulates the heck out of it. There's proteins wrapping around, causing these tubules to grow. And presumably that all has to do with these molecular levels. So to make a long story short, I'll just tell you the result and then I'll tell you the problem it poses for us. These are the coarse-grained models of the bar domain. Okay, you can see it's an ultra-coarse-grained model. There's a lot of protein in there. I forgot how many amino acids are in here, but there's quite a few. These helices are blue and white. The blue are easy to see here. In this model, I am represented by two beads. Okay, a full amphipathic helix. I'm represented by two beads, and so that's really aggressive. What I have done is, got the interaction of that pretty well with the protein, based on atomistic calculations. The rest of this comes from atomistic calculations. And this, by the way, is without those helices. So the so-called bar doesn't have the helices. And we can study these tubules and compare to experiments. These are these coats at very high density. They tubulate the membrane and they wrap them, so you can image that and we can recapitulate that behavior. But what we found with these results, and I want to use this to motivate for why we need to refine the model further. It's a very amusing and interesting behavior. It has to do with how many of these proteins you have on the surface. Okay, if they're in low density, so these are just a few of these. I forgot what this coverage is. This might be 20% or 15% coverage. They form strings. No one ever predicted that they would do that. I just showed you tubule coats. I think everybody thought that they would, even if they were low density, would start pulling off these tubules and coating them in sort of like a ram's horn or a unicorn. But we are predicting now that at low density they actually form strings, and then they create these very important bulges of the membrane. In cellular behavior, you get endocytosis, you get a bulge of the membrane going either from the action of proteins or some other forces. And these things are recruited to the neck of it. So this behavior is completely something different. At high density, this movie is my favorite movie. It shows how far we've come. This is effectively 1 billion atoms. So these are lots and lots of these proteins on here. I forgot the coverage. It doesn't look random, but it is actually. They're randomly oriented. It's just so densely packed you can't avoid the look of a lattice on here. You'll see what it does. It tears this thing to pieces. Okay. This is a coarse-grained simulation. You see it's tearing the liposome together. You see the spiral coats like I showed you before. So at high density, we get this behavior. Okay. What's the problem? This illustrates how we need to go to the next level of modeling. We start by assuming a certain bound density of these, right? In reality, what's happening is the proteins are in solution, they're binding and debinding, right? There's a dynamic process. And when they bind to the membrane, they don't just stick with one blow, right? There's a process of searching and trying to understand how to bind. And that's really not in our model. Our model is pretty primitive, okay? So we cheat. We start out either low density or high density, we get these beautiful results. The question is what really happens. Well, what really happens is something much more complex. And that is these helices, which I'm representing by these beads here. This is a free energy surface of just the helix. I don't have the full protein here on a membrane. And in different places, so this is a highly bent region, this is a flat region. This is on the flat surface. You can see this is hydrogen bonds and alpha-beta similarity. So in this region is a helix, okay? This is unstructured here. This would be some sort of a hairpin way up here that I'm not showing. We have all kinds of unstructured regions. You see those are free energy minima. And when you're on the flat surface or in solution, this is not very deep, right? This is actually the deepest minimum. When I'm folded into this nice region here, just like these red circles here, by the way, show packing defects in the lipids. They're not real particles. What they represent is how this thing fits into the membrane. You can see it's nicely folded. That's this free energy. So this is on the surface. So what's really happening here, what needs to be treated in this modeling is this what we call multi-state behavior. So those beads need to actually understand where they are in the membrane or the solution and have that interaction with the membrane modulated according to something like this, right? So you could argue at a minimum I need two states. I need one sort of unstructured state, which if I sort of join all those together, and one folded state. And then those sort of how they interact with the membrane have to be modulated by the distance of the membrane, and that's not in the model. So that's where we want to go with this kind of modeling, and I'm going to have to skip, unfortunately, there's a similar story to tell you about actin filaments, and I don't want to run out of time because I want to leave some time for questions, but you see this problem coming up again, that if I look at my coarse-grained representation of actin and look throughout the filament, I get an incredible span of effective interactions, a diversity. So there's substates in here, right? This monomer is different from that one at any given time, and how they interact both within themselves and with each other has a distribution. It has a set of states. It's not just a single, like a Newtonian particle, right? It's a set of states. So that leads me to the final part of this talk, which is where we're ending up with the theory. And this is probably the most conceptually difficult. I will point you all to the paper that just came out this year. It's the beginning point of taking everything that we develop. And again, tomorrow you will hear a lot more about time to the atomistic scale. So building in more and more of that atomistic information of what I just told you about. We need now a theoretical framework to generalize our approach to take all that physics into it and keep moving forward. And so this is this ultra-coarse-graining. I bring this slide up again. The fundamental problem now is simple and complex. It's simple in the sense that I want to represent my proteins, either one or many of them, by a very reductionist picture. But what I can't do anymore is assume that within those coarse-grained particles there's nothingness. Okay, there's just a point. Okay, there's some stuff in there. There's a whole world of protein that's living inside of there. All right, and we have to understand how to describe that. So let's take actin. What I'm going to do is show just the four, just to simplify this. I don't want to go to the more elaborate model. I'm just going to take these four. Let's think about what's happening in a concrete way, what we know about actin. Well, in this particular bead, which is roughly a fourth of the protein, we know there's one structural element that's very, very important. There's this loop. You can kind of see it here. It's called the DNase 1 binding loop, which is not important. We call it the D loop. It can be folded or unfolded. It actually can, unfortunately, be a number of configurations in between, but definitely folded and unfolded. So one way to think about this is we need to develop a framework where that bead understands somehow that what's inside of it is folded or unfolded, right? That in turn modulates how it interacts with the other ones and in different proteins. So it must get feedback from the others, so they have to be linked, all right? And also in actin, there's an additional picture which is not quite the same as living inside the beads, but we have this nucleotide, and it can have 3 different states. There's ATP, once it's hydrolyzed, there's ADP with the phosphate group is still bound in here. There's incredibly important electrostatic implications depending on what states they're in. And then it releases the phosphate group, we have ADP. And so on top of stuff happening in the beads, there's a kinetics going on, and it's very important, these conformations, to facilitating that kinetics, so it's coupled. So you can see the model, the physics, is getting more complicated. It's still simple. In other words, this is not trying to describe 375 amino acids, or actually, millions of them in filaments. It's just recognizing that it's not a Newtonian object with 4 beads, interacting with a simple potential. That's just simply too straightforward. So how do we do this? Well, this involves a kind of a merging of 2 areas of multiscale modeling. And Anton Sinitsky on Wednesday will tell you about the so-called Markov state models. His wife just had a baby. This is a dedicated student. I keep telling him, don't come back. Your wife needs you. Your wife needs you. I think he's going to come back. But if he does, it's not because I told him he should. She had a baby, I think, on Sunday or Saturday. So we're blending 2 things here. So the particle-based coarse grain is what I've been telling you about, right? Of this simplifying the structures of the systems into things that look like new particles. In a whole sort of another area of work in multiscale modeling is what we call discrete state or network theory or Markov state theory, where you imagine that your landscape has states, okay? And so this is a protein folding, and it's a Ripley thing, and you understand the kinetics of transitions between these states. There is some loose connection between these conformations and these states, but there doesn't really have to be. In other words, these are general things that describe kinetically that the whole protein is in a certain conformation, all right? What we're trying to do is put these together. Why? For exactly the reason I just told you about. We want to have states either living in the beads or overall a molecule, but we still want to spatially resolve where they are, okay? So it's essentially having a coarse-grained model with states inside it, and they know about each other. So this is the work that has recently done. The way we think about this, probably the mathematics is too complicated to go into in detail. If any of you are really seriously interested in this, all of the co-authors of this paper are here, and you can talk with them. The idea is that we imagine a superposition of states. And so this is something, if you've ever done or studied spectroscopy, you'll be able to understand this. Is sometimes you'll get a peak that looks like this in your spectrum, right? It's really very difficult and probably not right to try to view it as something that's in one state until you get here, and then you arbitrarily cut it, right? And then now I'm in the blue state. You really should view it as overlapping peaks. So literally in a spectrum, you have a spectral peak, and another one, they overlap because the dynamics of the system causes that to overlap. So it's a deconvolution. So this is the approach we have taken, that we allow these states to overlap, but we project them out by using the conceptual tool of what's called a bias potential. So the coarse graining that I told you about earlier is generalized to include these bias potentials to take a very complex state space, right? A space of all these molecular configurations, and project out of it to different states. And I won't have time to do this, but this whole force matching apparatus that I told you about for the water, okay, can be generalized. And it's subtle because you have to wait over these state probabilities, but from a single unbiased simulation, you can project out the data from these states. And I guess I won't, what was that? What I had cited the papers. This paper, which just came out this year in Journal of Chemical Theory and computation describes at least the theoretical basis for that. It's pretty heavy rating. What we're working on very, very hard now is to develop algorithms to bring it into practice in a I hate to use the word simple, it'll never be simple, but in a way that can easily be done, that's not just conceptual. And the first pass on that goes to this issue of actin, just to show you. If you look at the distribution of this, there's a dihedral angle here that tells us about the conformation of this protein when it's either free in solution or when it's in this filament. And if I think about this, how do I, and if I view that these beads represent the 4 domains, what that torsional interaction tells us is basically some sort of a force field for the kind of conformations they're in, right? But you can't treat it that way because there's all kinds of protein stuff that goes on inside there that makes it complicated. And so this is the way that we're approaching this. This is a distribution of that dihedral angle. It's a little hard to read here. So this is, if you do an MD simulation, you see this kind of distribution. And so projecting out these states uses what's called a Gaussian mixture model. You can see that we can sort of approximate this peak. There's a little bit of a failure to get it right here by 2 Gaussians. You can hardly see the green and the red. And we're able to do that for the different states. So this is ADP plus the phosphate, and ATP. And you can see the different Gaussian mixture models. And to make a long story short, what we can project out now using this approach is that depending on the nucleotide, we actually get different states inside of these beads. So the ATP has basically sort of this is ATP. There's one major state. It's a flattened state. There's a couple of minor states. With the phosphate group, there's an intermediate state that's sort of favored. And what's most important is ADP. There's actually 2 states. So when you have ADP in this nucleotide here, this has a bimodal distribution. Okay, so because of the protein interactions in here, it actually has 2 possible states, and we can project those out. I won't go into all the biochemical and biophysical details of that. We think it's very important to how that forms filaments. Okay, it's a switch. It's able to switch for when it binds and starts polymerizing in the filament. So that's one of the things. Anyway, I will wrap up. I want to leave a little bit of time for a few questions. I've got multiple acknowledgments here because so many people have participated. The first, I have to thank all of my collaborators. You're going to hear from, I think these 3 guys are going to all sort of speak. Martin and James will be very instrumental in dealing with our hands-on workshop. This is Anton, who got the baby, so if he shows up, his wife will be probably mad at him, but I think he's going to. He's a very serious guy. This is a list of other collaborators. I just happen, it's never good to not acknowledge your collaborators. Other students, John Grime is really been important, and we have many collaborators. So thank you very much for your attention. I'll be happy to answer some questions. Of course, we can talk anytime during this workshop. Thank you very much. Yeah.
My question is about the sampling. Is the sampling issue have resolved for this kind of coarse-grained?
The sampling of the coarse-grained model, or the sampling of the atomistic data?
The coarse-grained. I mean, the sampling is an issue for atomistic data. What we get if we get enough sampling. So is it solved for coarse-grain, or is it still an issue?
So it's easier for coarse-grained models because typically the interactions are smoother and they represent the large-scale degrees of freedom. However, if you push that model to scales that involve thousands of proteins interacting with it, you still get a sampling problem. I could probably say that the sampling problem is not solved for any problem that anyone works on, anywhere. Okay? the sampling problem is the simple problem, right? And you know, I think even I just read a paper briefly this morning. People have been debating about water and whether there's two coexisting phases. And there's a new paper that came out that really all of those people who claimed there were these two coexisting, there was a high density and low density phase of water that's just sampling. They're just not doing good enough sampling. The different kinds of sampling, you haven't run long enough, you're stuck in slow modes, or you have finite size problems, so your system's not big enough. But even something as simple, I think liquid argon is well sampled, I think, if we do that simulation. But almost everything, sampling is one of the hardest problems there is. In the coarse-grained models, by definition, they enhance sampling. That's one of the reasons for them. But when you push them to very high scales, then the sampling problem.
Yeah. So when you generate this coarse-grained model, do you still have to perform the atomistic simulations on the entire system, or can
No, of course that would. The whole point is that you wouldn't be able to do that, right? When you develop the coarse-grained model, you hope to use relatively limited atomistic simulations to feed into it. If you end up having a system where they're the same size, what the coarse-grained model will do for you is push the time scales that you can access way, way out. But almost always what we want to do is use a more limited atomistic simulation and then achieve scales that we couldn't even get at. The HIV capsid is a good example. That is, so a paper just came out in Nature where they did do an atomistic simulation of it. I think it's 60 million atoms with solvent. And they were able to run it for about 100 nanoseconds. So that shows you, I mean, we do that very routinely and quickly. And you know, they'll always kind of catch up as the computers get bigger. But we are orders of magnitude beyond that.
Right. So when you like make the model itself, do you like perform the atomistic simulation on a part of the system, or?
Yeah. We do as much as we can, right? The thing that makes me happy about all these advances in atomistic simulation is, you know, we'll use everything that they can do. So better sampling, the better computers, the better scale of algorithms. I'm happy for all of that because we'll always feed that in and just allow us to do bigger and bigger things. Yeah. There are some problems. I will say, since you asked that question, let me come back. I think it's an important question. Where I don't think, I actually am a little bit less optimistic now about this scrolling has got me confused here. I'm less optimistic these days, even though early on we spent a lot of time working on it. There we go. I'm less optimistic about these higher resolution coarse-grained models. So you see, this is a model where in this case, I've taken each amino acid, mapped it into two beads, one for the backbone and one for the cytosine. I think atomistic simulation is just keeps catching up. The ability to study this kind of peptide or 100 of them, you know, what we can do today versus what we could do 5 years ago is dramatically greater. And I don't think that coarse graining at this level of resolution buys you that much. In fact, it actually buys you some complications because every one of these amino acids, here we have force fields, you know, for better or for worse, we kind of trust them, we're certainly improving them. Here, these objects now have a new kind of diversity of interaction. If there's a lot of them, it's hard to capture all of that, okay? So I'm going to hate to be like killing a field that I helped to start, okay? Generally a bad idea to do that, but I think this higher resolution coarse graining is getting caught up by the atomistic simulations constantly. So that's one of the reasons I believe that the ultra-coarse graining, so where you really are doing a lot of protein sort of the last part, I think that we always stay way out ahead of where the atomistic simulations are going. So, and you know, our objective, I don't believe we'll ever be able to simulate a whole cell, you know, all the stuff going on in there because it's so complex, but I'd like to have that capability possible. You know, maybe it would be a bacteria or something simpler than a eukaryotic cell, but in atomistic simulation. Any other questions? Yeah.
So related to this question, you said you sort of like simulate the all atom thing in like pieces. Is it obvious that, particularly with the free energy, you can do that?
No.
That the
I
free
think
energy of
that's
the
a
thing is the sum of
that's an excellent point, and it actually touches on a larger point, which is what we call transferability. So, the question of can I simulate a piece and then just additively build it, or that's part of another thing is can I simulate the whole system but in certain conformations and then assume that it describes other conformations very well. So this whole issue of the transferability of pieces of the coarse-grained model to newer, larger pieces is a very fundamental one. And so, your answer, the answer is no, it's not obvious. I think that part of, if I can pull up my Uber diagram, part of the reason, or I'll find it soon enough, there it is. Part of the reason that we're so keen on taking the coarse-grained model and then diving back downward in scale is to really explore what we've done with the coarse-grained and be sure that the atomistic interactions recapitulate that or improve upon it. But I think you have touched on a very fundamental question of transferability. And one way of thinking about it is I think it's, at least from a pure theoretical point of view, it's impossible to have transferability, in other words, precise transferability, that I could do these building blocks and stick it together without some ramifications. But I do think there's room for very good theory to be done. Like, how do we understand when we put pieces together, how does that recapitulate formally the big system, and what do we know would be the errors, what should we focus on fitting these things? We shouldn't make it sound like it's a problem with just what we do. I mean, look at atomistic force fields. People do this all the time. They do some calculation on a fragment, they stick it in a bigger force field. They assume something that works well for this protein will work well for any other protein. Right? I mean, we've gotten very comfortable with assuming you just take charm or Chromax, run it, and everything's great. But all the data is showing it's not. So the transferability, there's only one thing that's transferable, and that's Schrodinger's equation. We think. As long as the energies aren't too high, right? And huge amounts of sampling at finite temperature. No one's doing that. The best people try are these ab initio molecular dynamics. Those are very limited. So.
And one other thing I was wondering is, like, do you have any way of like guessing how the system will respond if you like change the conditions, like ion concentration or temperature or something? Because nominally you'd have to like go right back to the all atom simulation again.
Nominally you would. There is a James, who's the first author of this paper, worked out a theorem for our coarse-grained force fields that show their sensitivity to the underlying parameters. So that's a little bit different than if you change composition, right? But that theory is if I change the charges or the Wiener-Jones interactions, it tells you, it's very equivalent if you know there's a theorem called the Hellman-Feynman theorem in quantum mechanics that tells you how the energy changes if you change the parameters in the model. This is like that. So I think the theory could be generalized to do what you say. We definitely know how to do it for temperature. We already published a paper. That's fairly simple. Temperatures are reweighting in these states. But other stuff, like if I change salt concentration, in principle that's a very non-additive complex effect.
Are the all atom potentials temperature dependent? I forget. No? Okay.
Well, I think so, but they're not. I mean, you're supposed to be able to use them. Most of them parameterized for easily 308 Kelvin.
Okay.
Yeah. They shouldn't be temperature dependent, probably.
Because then it's not just the same way.
The thing that helps you there is at the all-atom level, you're on the Born-Oppenheimer surface. And the excitation gap to the next electronic state is enormous relative to KT. So temperature sensitivity shouldn't be that much. Why it's hard is that in the parameterization of force fields, people didn't run them at temperatures that visited fluctuations that might be visited at high temperature. Like water is a perfect example. There's tons of water force fields that are good around 300 Kelvin, but they're not good at all once you get away from Okay, yeah.
So these coarse-grained which are normally used in heat for sampling, is there, if you or anyone else doing it with like maybe Monte Carlo or any other sampling?
It's interesting, the Monte Carlo is not used at all for complex heterogeneous systems because your move rules are very complex. The best you can do is what's called force bias Monte Carlo, which is very similar to MD because MD is force bias. If you had a coarse-grained model where you had a relatively few number of interactions and a relatively few number of length scales associated with those interactions, I think Monte Carlo would be a great way to do that. If you just wanted to simulate the structure. An example I can imagine is suppose you did amyloid aggregation and your peptides were represented very aggressively in some simple way. You probably don't. But we haven't, the MD stuff is pretty highly evolved.
You mentioned some of the difficulties like with the water and leading to implicit solvent. I'm curious, with all the glossing over, you're doing a lot of the high frequency interactions. What type of time steps are you looking at?
So, we're not glossing over them, we're averaging over them. Yeah. Glossing is, those are what the other guys do. We don't gloss. Okay. So I'm just making fun. We do one. So if you're really doing coarse graining well, and you had an extremely good way of identifying the high versus low frequencies, then you would average over those high frequency fluctuations. The time steps, it's a subtle point. In water, when you go to the 1-beat water, you can boost the time step by, I think, a factor of 10 over, even over rigid water, right? It's more over flexible, because flexible's got these OH bonds, they're incredibly high frequency. At the other levels, the things are so coarse-grained that the time step doesn't have such a meaning. The time in those models is a sampling parameter. The actual dynamics in those coarse-grained models is very hard to relate to real dynamics. So that it's not clear that the time step, it's like if I told you, okay, the time step is a picosecond, that means that much, right? The time step is what it is in the integrator. What you have to look at is what you're sampling in your simulation. So if we see the whole formation of an HIV capsid, which we haven't, but we're hopeful, that takes, I don't know the actual biological time scale, I'm not sure anyone does, but certainly seconds, not minutes, hours. So it's a lot of big boost in time. You hit a point which I haven't talked about, but one of the real holy grails for the future, in addition to these other elaborate problems, is having a coarse-grained model where the time really means time. So if I'm an experimentalist, I'm doing a single molecule experiment. I study diffusion of something on a membrane, and I simulate it. My time is the same as the experimentalist time. That's not trivial, but the equations of motion are not really understood yet. And I think that, and the kicker on that is, I think I understand how to get those equations of motion, but you make the algorithm so much more complicated that you slow it down. So you start defeating the purpose of the coarse graining. So the holy grail, if I'm lucky in my lifetime, will be a super efficient algorithm that does all this beautiful stuff with coarse graining and is meaningful in time. So when that's done, then we can all rest. So. Okay, we should. No, I'm cutting into the coffee break too much. We're happy to answer questions. So we have a break.